In our previous discussion, we derived an expression for strain energy density of an anisotropic material. We will continue with the same discussion and try to derive a strain energy density of an isotropic elastic material. We will develop constitutive equations for isotropic elastic material, and finally, we will discuss plane stress and plane strain problems. So on the screen, we can see the strain energy density equation for an anisotropic material. For the case of isotropic material, depending on the principal strains, we can reduce this equation to something shown on the screen over here, which says that the strain energy density is equal to half C11 epsilon 1 square plus C12 epsilon 1 epsilon 2 plus half C13 epsilon 1 epsilon 3 plus half C12 epsilon 1 epsilon 2 plus half C22 epsilon 2 square plus half C23 epsilon 2 epsilon 3 plus half C13 epsilon 1 epsilon 3 plus half C23 epsilon 2 epsilon 3 plus half C33 epsilon 3 square. Please note, this strain energy density equation is written for the principal directions, or in other words, for the strain's principal direction. So that means that the only strain which would be remaining will have coefficients strain 1, strain 2, and strain 3. That in the equation, we have got only the principal strains appearing. In the case of isotropic elasticity, we can make the constants C11, C22, and C33 equal to C1, and the remaining constants C13, C21, C12, C31 equal to C2. We discussed previously that in isotropic formulation, we can have only two constants. So those are shown over here. Please note that the expression of strain energy density, which we have written over here in the form of principal strains, that is valid for isotropic as well as anisotropic material. Once we plug these constants in our strain energy density equation, then it will be confined to isotropic material. These constants can be plugged into this equation. After algebraic manipulation, we can get the form of the strain energy density equation for isotropic material as equal to half lambda small brackets strain 1, strain 2, strain 3 whole square plus G times strain 1 small bracket strain 1 square, strain 2 square, and strain 3 square. Over here, our lambda is equal to C2 and G is equal to C1 minus C2 by 2. So in this equation, if we put the constants in the form of lambda and G and try to complete the squares, we will get this form of strain energy density. The coefficients lambda and G are called Lamy's elastic coefficients. We can get the strain energy density equation in terms of strain invariance also. So just to remind ourselves of strain invariance, in our principal strain discussions, we said that we can have the strain at a point expressed in the form of characteristic equation, and from there we can get the characteristic equation. From there we can get three different types of invariants, and please remember these invariants are constants. I1, I2, and I3 are called invariants because they don't vary with the orientation of the coordinate axis. So our invariants looked like this one, like the I1 equal to strain 1,1 plus strain 2,2 plus strain 3,3, or this is so-called the volumetric strain. And the second invariant looked as strain 1,2 square strain 1 3 square, strain 2 3 square, minus strain 1 1, strain 2 2, minus strain 1 1, strain 3 3, minus strain 2 2, strain 3 3. So the second invariant dealt with the shear strains, and the first invariant dealt with the axial strains. So we can bring our strain energy density in terms of I1 and I2. Over here I've called it I1 prime, I2 prime, but it's the same thing. And we get our strain energy density equal to half lambda plus d g I1 bar square plus 2g I2 bar square. Now, just to remind ourselves that this strain energy equation is in the form of principal strains. That's why we don't see any shear strain appearing in this equation. We can also write this equation in terms of shear strain, and we get something like the equation shown, which says that the strain energy density is equal to half lambda small bracket strain 1 1 plus strain 2 2 plus strain 3 3 whole square plus g times small bracket strain 1 1 square plus strain 2 2 square plus strain 3 3 square plus 2 strain 1 2 square plus 2 strain 1 3 square plus 2 strain 2 3 square. So in this strain energy density equation, we have the shear components also appearing. That means to say that it's not with respect to the principal direction. So it's the same equation as discussed previously, and we have written it as it is and introduced the constants lambda is equal to C2 and G is equal to C1 minus C2 by 2. So they introduced the Lamés constant, so that makes this strain energy equation exclusive for isotropic elastic material. In our previous discussion of elasticity and internal energy density, we derived these stress components, which says that sigma 1 1 is partial derivative of the strain energy density with respect to strain 1 1. Sigma 2 2 is a partial derivative of strain energy density with respect to epsilon 2 2, and similarly sigma 3 3 is partial u naught by partial epsilon 3 3. Sigma 1 2 is equal to half partial u naught by partial epsilon 1 2. Sigma 1 3 is equal to half partial u naught by partial epsilon 1 3. And finally, sigma 2 3 is equal to half partial u naught by partial epsilon 2 3. So we can take the partial derivative of the strain energy equation and get our stress components. So that is, these expressions are again written over here. And once we do that, we get sigma 1 1 equal to lambda times E plus 2g epsilon 1 1. Sigma 2 2 is equal to lambda times E plus 2g epsilon 2 2. Sigma 3 3 is equal to lambda times E plus 2g epsilon 3 3. The shear components are sigma 1 2 is equal to 2g epsilon 1 2, sigma 1 3 is equal to 2g epsilon 1 3, and sigma 2 3 is equal to 2g epsilon 2 3. Please note that E, small e appearing in the stress components is actually small displacement volumetric strain, and that is equal to epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. G is the constant which we have already defined previously, so this is one of the Lamés constant. Again, lambda is Lamés constant. Now we can work out the same equation in terms of strains. Please note that these stress components are actually, please note that these expressions are actually relating stresses with strains. So these are constitutive equations. These constitutive equations can be brought in terms of strains, and by inverting these stresses, we get epsilon 1 1 equal to 1 by E small bracket sigma 1 1 minus nu sigma 2 2 minus nu sigma 3 3. Nu is another constant, and we will define what nu is. Epsilon 2 2 is equal to 1 by E small bracket sigma 2 2 minus nu sigma 1 1 minus nu sigma 3 3. Epsilon 3 3 similarly is equal to 1 by E small bracket sigma 3 3 minus nu sigma 1 1 minus nu sigma 2 2. The shear components are epsilon 1 2 equal to sigma 1 2 by 2g, which is equal to 1 plus nu by E sigma 1 2. Epsilon 1 3 is equal to 1 by 2g sigma 1 3, which is equal to 1 plus nu by E sigma 1 3. And similarly, epsilon 2 3 is equal to 1 by 2g sigma 2 3, or that is equal to 1 plus nu by E sigma 2 3. Now, we will get these expressions if in our stress expressions we plug value of E equal to G times small bracket 3 lambda plus 2G in numerator divided by lambda plus G in denominator. So if E value is put as this one and nu value is put as lambda by 2 by lambda plus G. G is more commonly called as modulus of rigidity, and it is purely related to shear. So normally we have the shear formula tau is equal to G gamma, and G is called modulus of rigidity. E in this expression is called as modulus of elasticity. Stress is equal to E times strain. So that appears in the Hooke's law. And E in terms of lambda and G is written as shown over here. Nu is Poisson ratio, and that is the ratio of lambda by 2 times small bracket lambda plus G. Please note that in the case of constitutive equations, we have got stresses appearing on one side and strains appearing on another side. If we are trying to invert the stresses and work out our strains, we have to make sure that again, on the left hand side, we have got the strains appearing, and on the right hand side, we have the stresses. If we assume the first equation and think that how we get it in terms of stresses, what we have to do is in the stress equation, we plug the value of E, which is epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. Take epsilon 1 1 as a common factor on the right hand side. We would have epsilon 2 2 and 3 3 also appearing in this expression, which we want to convert into stresses. So for that, we will have to resort to these other two equations, get the value of epsilon 2 2 and epsilon 3 3, plug that in the first equation, and get everything in terms of stresses. In the meanwhile, we will have the constants appearing in this form. We can repeat the exercise for all of these stresses and get our strains in terms of stresses. We can also get the stresses in terms of E and nu, and that has been shown over here. So sigma 1 1 is equal to E by 1 plus nu small bracket times 1 minus 2 nu small bracket, and everything is in denominator. Times the big bracket, small bracket 1 minus nu times epsilon 1 1 plus nu times small bracket epsilon 2 2 plus epsilon 3 3. Similarly, epsilon 2 2, epsilon 3 3, epsilon 1 2, 1 3, and epsilon 2 3 can be derived in terms of E and nu. So these stresses have been derived in terms of constants E and nu over here. Now, generically, we can write our shear and normal equation. So shear strain Ij when I is not equal to J is equal to 1 by 2 mu into sigma Ij. and 1 by 2 mu is also equal to 1 plus nu by E. And that is coming from these two equations. So this is the expression of strain Ij when I is not equal to j. In other words, it's a shear strain equation. The second one is normal strain, which is when I is equal to j, and the strain Ij will be equal to 1 by E sigma Ij minus nu by E into 3 sigma h minus sigma ij. Sigma h is hydrostatic stress, which is equal to sigma 11 plus sigma 22 plus sigma 33, everything divided by 3. So we can get any equation by plugging the value of I and j in this equation. So if I is equal to j, then we can see that this strain expression reduces to the expression which we derived previously, which looks like this. When I is equal to j, we will get exactly these equations. So this is just a general form of the top three equations. These equations come very handy when we discuss plane stresses and plane strains. Similarly, we can have a general stress equation, which is sigma ij equal to 3 nu divided by 1 plus nu into sigma h delta ij plus E by 1 plus nu epsilon ij. Now, sigma h is the hydrostatic stress, as we discussed. Delta ij is actually what's called the Kronecker delta. In the case of Kronecker delta, if I equal to j, then the value of this small delta ij would be equal to 1, and if I is not equal to j, then it will be 0. So delta ij is actually a component of an identity matrix. Normally we would have a 3 by 3 identity matrix whose components would be traced by delta ij. So this equation is nothing but a general form of the stress equation in terms of E and nu derived over here. So it's just a general equation of stresses and strains. If I is equal to j, then we will get axial stresses, and if I is not equal to j, then we will get shear stresses. So this equation captures the stress equations in terms of E and nu. Now in this equation, we can write the value of sigma h, which is the hydrostatic stress, as lambda times epsilon v, and bulk modulus times 3 nu divided by 1 plus nu is equal to the Lami's constant lambda. Now the question is, how do we get this bulk modulus? So if we assume the same stress equation, sigma ii is equal to lambda epsilon v delta ii plus 2 mu epsilon ii. We write it corresponding to three axes of the coordinate system, which is I, j, and k, or in other words, 1, 2, and 3. So we write the three expressions, we add all of them. This will be stress sigma 11, sigma 22, and sigma 33, which is actually a hydrostatic stress. And these three will add up to 3 times lambda epsilon v, which is the volumetric strain, and plus 2 mu epsilon v. Taking epsilon v common, we get 3 lambda plus 2 mu. If we define P equal to the hydrostatic stress by 3, where P is the mean stress, then plugging value in this equation, we get P is equal to lambda plus 2 mu by 3 epsilon v. So this everything is in epsilon, and this lambda plus 2 mu by 3, that is equal to the bulk modulus. Please note that in this expression, mu is equal to g, which is the modulus of rigidity. So g is one of the Lami's constant, as we discussed previously, and that is equal to mu. So that appears in the strain equation. In this equation, our hydrostatic stress is equated to lambda times epsilon v. So we determined our hydrostatic stress equal to 3 times lambda plus 2 mu in small bracket times epsilon v, and worked out the so-called bulk modulus B times epsilon v equal to the mean stress. So in this expression, we have written B equal to lambda plus 2 mu by 3. We can convert this mu into nu by plugging the expression shown over here. Now in here, we have got lambda, and this G is equal to mu. We can work out our mu in terms of lambda and nu. And from there, we would get lambda equal to B times 3 nu divided by 1 plus nu. That is plugged back in this expression, and we get lambda times epsilon v delta ij plus 2 mu epsilon ij. Now we will discuss boundary value problems in solid mechanics. Consider a body B shown in this figure, which has got prescribed displacements over part of the body shown AD. So AD is that area where displacement is prescribed, and AN is that area where traction or forces are prescribed. So the example of this can be a beam subjected to external load. So external load is a traction or a stress which is prescribed, and there can be an yielding of the support of a beam, which is a displacement prescribed. So this is a simple form of a body beam, and generically it is shown over here, a body B having displacement and tractions specified. This body has got a body force which is shown by B. So the boundary value problem of linear elasticity is specified by the following equation. We have got the first equation, which is our equilibrium equation, and that is diversion of S plus B equal to 0. So this we have previously derived. So this is the same equation which is shown over here, the equilibrium equation. S is equal to S transpose. In other words, our stress components, 9 stress component tensor, that is equal to stress transpose. So these are our stress components, 9 stress components, and if we call this tensor as S, S would be equal to S transpose. Inverted A means for all. So this diversion equation or this equilibrium equation is valid for all X which is a member of this body. So there is a function within this body. So 5b actually defines this body. It's a function which defines this body, and X is any point within this body. So we are saying that the equilibrium should be satisfied at each and every point within the body. The second equation says that stress at each point must be equal to the stress transpose tensor. So stress tensor is equal to stress transpose tensor. That is what the second equation is saying. The third equation is the strain tensor, which is equal to half of the displacement tensor or the gradient of displacement tensor plus gradient of displacement tensor transpose. So previously we had this displacement tensor. We defined our strain as equal to half of the displacement tensor plus displacement tensor transpose. So instead of H, now we have called it U. Earlier, we defined our stress sigma equal to lambda trace of epsilon I plus 2 mu strain tensor. So this is the same equation which we just derived. So stress, which is S written over here, in this case, component wise, we have written sigma is equal to lambda time epsilon v. So epsilon v is actually equal to epsilon 11 plus epsilon 22 plus epsilon 33, and tr epsilon means that we have to add epsilon 11 plus epsilon 22 plus epsilon 33 and times the identity tensor. So this is the identity matrix which we discussed. Delta ij is its component, and that plus 2 mu strain tensor. We have got three equations for this one. We have got 6 equation over here, and we have got 6 equation over here. So altogether we have 6 plus 6, 12, and plus 3, which makes it 15. How many unknowns do we have? We have got 6 stresses unknown, 6 strains are unknown, and 3 displacements in x1, x2, and x3 are unknown. So 6, 6, 12, and 15. These are 15 equations, and we have got 15 unknowns. That means to say that this is a determinate problem. Now, all these equations are valid for this body, which is 5b, and these equations are also called as governing differential equations. These are all differential equations. Now, beside this, we have boundary conditions. As we discussed, we have a displacement boundary or a force boundary condition boundary where we specify displacement. That is called Dirichlet boundary condition. And the displacement where we define force or we apply force, that is called Newman boundary condition. So the Dirichlet boundary condition and Newman boundary conditions are applicable for any x on the surface area, as we know that displacement is applied on the surface area of a body, and similarly the forces are applied on the surface of the body. That's why we specify the boundary conditions on the area, whereas the equations over here, the governing differential equations, they are all defined on the whole volume. So phi b is actually the volume of the body, and phi a is actually the area, the surface area of the body. So from this discussion, we can realize that the problems in solid mechanics require 3 basic components. The first one is equation of geometry or deformations, which is this one, relating the displacements to the strains. The second one is equation of equilibrium, which is this one, relating the applied tractions and body forces to the stresses. And the third one is equation of constitution relating to stresses and relating stresses to strains. And that is these ones. So these 3 are the main equations which are used to solve any problem in solid mechanics. Thus, all these equations are necessary to the statement of mechanics problem, like, for example, bending of a beam, torsion of a bar. However, they are not sufficient to solve such problems. In addition to these equations, which describe what is happening inside the body, we must also describe what is happening on the surface or boundary of the body. These boundary conditions generally comprise given data about the displacements and the applied tractions on the surface of the body. The combination of these domain equation and the boundary conditions is called boundary value problem. Over here, it is important to appreciate that we have called the forces which are applied on the boundary as traction. So traction is different from stresses. Stress has got 9 components. Traction is the force which is applied at a particular phase of the body. So, for example, in case of a box like this one, traction would be related to all the forces per unit area on the face of the body. The stress is actually a tensor which is having 9 components, so that include all the faces of the body. And how can we determine traction from stresses? That is very straightforward, and we have to multiply the stress tensor transpose with the outward drawn normal at the boundary of the body. So we can take any normal vector on the boundary of the body, multiply the stress tensor at that point with the normal vector, we will get the traction at the boundary. So the example is that if we take this stress tensor, transpose it, and then multiply it, for example, with E1, which is 1, 0, 0. So E1 is actually the outward drawn normal in the direction x1. So we have got x1 over here. We have a unit normal E1. In this direction, we have got E2, and in this direction, we have got E3. The coordinate of E1 would be 1, 0, 0. If we multiply 1, 0, 0 with this stress tensor, we would get S11, S12, S13. All the forces per unit areas corresponding to the outward drawn normal 1. The first subscript is for the outward drawn normal as per our convention. Please note that S is equal to S transpose. So it doesn't matter whether we write S or S transpose. As we have started our discussion related to boundary value problems, that would be incomplete if we don't discuss plane stresses and plane strains. In this course, we will try to simplify our boundary value problems. Normally, we have 3D bodies as shown over here. We will assume that the stresses within these bodies is just within 2 planes rather than 3 planes. And in mechanics, in advanced structure mechanics, we adopt 2 different types of problems or 2 different types of formulations for solving plane stress and plane strain problems. We will discuss what is plane stress and what is plane strain in a bit more detail. Let's see what are the 2 different types of formulations that are adopted in solid mechanics. So the first formulation is displacement formulation, in which we would start from the displacement of the body, find the strain using the strain equation, which is shown over here, and then after that strain, we will work out our stresses. So we start from displacement, find the strain, and then use the constitutive equation to find the stresses, and that works out all the unknowns within the body. The second formulation is stress formulation, in which we start from stresses and we use constitutive equations to find out strains, and then we make sure that the strains we have got, they are compatible. So we ensure the compatibility equations. Please note that in the first formulation, we start from actual displacement, so therefore we don't need to satisfy the compatibility equation. The displacements we start from, they are already compatible with the body. So we don't need to satisfy our compatibility equations, that will automatically be satisfied. However, in the case of stress formulation, we have to satisfy our compatibility because we get strains, and there are more strains as compared to displacements. There are 3 displacements, one in x1 direction, another one in x2, and the other one in x3. 3 displacements, but there are 6 strains. So we have got more equations to satisfy and less unknown. That makes this problem an indeterminate one, and therefore compatibility provides some additional equations with which we can make sure that the strains and displacements are compatible. Displacement formulation is the more common formulation. It takes less time and it's very efficient. In finite element analysis, displacement formulation is employed.